We'll take a look. So for this first one, what I'm thinking is I have tangent of some stuff. I know the derivative of tangent of x is secant squared of x. So for this problem, if I'm trying to find the derivative of tangent of this stuff, my derivative is going to equal secant squared of that stuff. And of course, we have to multiply by the derivative of that stuff, which is going to be 4x cubed plus the derivative of 2 times e to the x. The constant multiple 2 hangs out, and the derivative of e to the x is e to the x. And that's it. I don't think you need to make this more complicated. I know some people like to do this whole thing where they like say the inside function is like g of x or u of x or something, and then differentiate the outside and say it's like secant squared of u times u prime, and then plug back in what u is equal to. That's fine, that works, but I think people doing that way are trying to make it more complicated than it needs to be. But I will point out, you could have said something like, yeah, sure. I would probably call it g of x is equal to x to the fourth plus 2e to the x. And now my function I can think of as tangent of g of x, and the derivative is going to be secant squared of g of x times g prime of x. Again, same idea, just making it more complicated. And then that's going to be secant squared of x to the fourth plus 2e to the x plus the derivative of g of x, which is still 4x cubed plus 2e to the x. It's fine to do it this longer sort of processy way, but again, my opinion is that's not really necessary if you're just given this function straightforward to differentiate. If you have other pieces, kind of, it can be a little more complicated. We'll talk about that in a little bit here. Looking at the second one, similar concept. I'm always looking for my outermost function. So here, my outermost function was tangent of some stuff. Here, my outermost function is being raised to the 9th power. I have some stuff to the 9th power. So my derivative is going to be, I don't really like writing it again, but I guess I will. The derivative of cosine of x plus 4x to the 7th to the 9th is going to be 9 times our stuff to the 1 less power. And then we have to multiply by the derivative of the stuff, which is going to be negative sine of x plus 28x to the 6th.
So you can't do it all at once. Like you can't take the derivative all at once.
I think you can do it all at once. I would say right here, I did do it all at once. And I would say also here, I did do it all at once. Writing it this way was more of a doing it step by step, where I first differentiated the outside function and didn't even think about what was going on with g or g prime, but still wrote it down. Yeah, I'm of the opinion that for the chain rule, you can almost always do it all at once. It just sometimes requires some careful thought. Let's look at some more examples. Yes. Where did 28 come from? Good question. So where that came from was the fact that when we differentiated 4x to the 7th, the derivative of that is going to be the 4 hangs out. And what's the derivative of x to the 7th? 7x to the 6th. So we get 4 times 7x to the 6th, and the 4 times 7 is 28. Again, really pointing out here this constant multiple rule, that if you take the derivative of a constant times a function, as I like to say, the constant just hangs out, and we multiply by the derivative of the function. And sometimes we don't even show that, like I didn't show that work in that step right there, but we certainly can. Good? Yeah. We'll do some more examples, yeah, sure. Some slightly simpler examples in some sense. Let's say our function is h of x equal to 4e to the 5x. In my opinion, e to the stuff always feels a little bit confusing because most functions, the stuff, the inner part of your function, the argument, usually is surrounded by parentheses, like it's sine of parentheses something, or it's a square root and of stuff that's inside the square root. in this example, the quote unquote stuff, which is 5x, just doesn't quite look like as much as like the inside of the function. It still is, but I just want to point out, I feel like it can be kind of harder to see that here. So if you want, there's nothing wrong with putting parentheses around whatever is in your exponent there. And then if we're going to take the derivative, well, the 4 is multiplied by a function of our variable, so it's going to hang out. And the derivative of e to the stuff is going to be e to the stuff, because the derivative of e to the x is e to the x. But then we have to multiply by the derivative of the stuff. And the derivative of 5x is just 5. And although people say you can leave things unsimplified, we should simplify this because it's really straightforward to do. The 4 times 5 gives us a 20. So we say this is equal to 20 e to the 5x. Why don't you all try this one? F of x is equal to 2e to the x cubed plus x. All right, so let's see. Again, constant multiples hang out. The 2 is going to stick around. The derivative of e to the something is e to the same something, but then we have to multiply by the derivative of that something, which is going to be 3x squared plus 1. Let's make it more complicated. Yeah, well, not too bad so far. Let's say we have our function is y equal to secant of x to the 4th power. Now I want to find the derivative. So you can either write, and so there's lots of ways to write this notation, right? And you can, I'm trying to kind of cycle through the different notations so you can see them all a few times. I often like to write f of x and f prime of x. Here I might write either dy dx for my derivative or y prime. They're both equally good. So here, you have to remember that the derivative of secant of x is secant of x times tangent of x. So the derivative of secant of some stuff is going to be secant of that stuff times tangent of that stuff. And then at the end of the process, we're going to multiply by the derivative of the stuff. So it's going to be secant of x to the 4th times tangent of x to the 4th times the derivative of x to the 4th, which is 4x cubed. Not too terrible. Why don't you all try this one? Let's say our function is r of x equal to cosecant of x to the 9th power plus e to the x. And I'll remind you, the derivative of cosecant of x is very similar to the derivative of secant of x. Derivative of secant is secant x tangent x. The derivative of cosecant of x is negative cosecant of x times cotangent of x. So you got a little bit of writing to do here. right, check it out. One thing I'll point out also, just for kind of what's the word I'm looking for here? Not notation, but like nomenclature or just the names you call things, the names of things. I would really encourage you all to say sine of x, cosine of x, not cos, cosine, tangent, not tan, etc., etc. So tangent, cotangent, secant, cosecant. I know it's an extra syllable. It's worth saying. It's going to remind you of what's going on, and especially, I can't say enough really how important the word of in mathematics is. The of is telling you, oh, this thing I'm about to say after that of is inside my function. It is the argument. It is the word that is letting us know, hey, this is the piece that's the inside that you're then going to take the derivative of after you've done the rest of the chain rule. So we have cosecant of x to the 9 plus e to the x. Our derivative is going to be negative cosecant of the same thing times cotangent of the same thing. And then we have to multiply by the derivative of that same thing, which is going to be 9x to the 8th plus the derivative of e to the x is still e to the x. Cool. All right. So chain rule is what it is, but now we're going to try and start kind of mixing all the rules together. So any function can be differentiated through a mixture of using the product rule, the quotient rule, the chain rule, in addition to the rules for all the derivatives. Power rule, derivative of trig functions, derivative of x. There's still one other function which we'll get to today that we haven't learned how to differentiate yet that's on my mind. We will get there, I think, today, though. So, for example, we could say, I want to find the derivative of y equal to x to the 5th plus 1 to the 8th power times cotangent of e to the x. And now, in addition to having to use the chain rule, we're also going to have to use the product rule. So what I see at kind of the get-go here is that I have a function, x to the 5th plus 1 to the 8th times another function, cotangent of e to the x. And if it's helpful, it is always totally okay to label these as like f and g if you want. So that you can remember, oh yeah, the product rule says it's going to be f prime times g plus g prime times f. So when I start taking the derivative, so first f prime, okay, well, for the derivative of x to the 5th plus 1 to the 8th, I have to use the chain rule. I have some stuff to the 8th power. My derivative is going to be 8 times that stuff to the 7th power times the derivative of the inside stuff, which is 5x to the 4th. There's my derivative of f. And then we still have to multiply it by g, which is just cotangent of e to the x. And then we add and switch it up, right? Or we vice versa it, right? We do the other thing to the other thing. So now we're going to leave f alone. It's going to be x to the 5th plus 1, the 8th power. And we're going to multiply by the derivative of g. So the derivative of cotangent of some stuff. So here's how I remember it. I know the derivative of tangent of x is secant squared of x. So the derivative of cotangent of x is cosecant squared of x with a minus sign in front. Because it's a cofunction, all the cofunctions get a negative. So we're going to get times, I need a parentheses here, negative cosecant squared of my stuff, which is e to the x, multiplied by the derivative of my stuff, which is also e to the x. And there's my f, and there's my g prime. You do not need to label these things this way, but if you find it helpful to label them, it is totally fine to label them. Before I forget, let me pass around the attendance sheet. You remember to do this thing? So let's look at a similar-ish example. In fact, I'll have you all try this next one. So let's say our function is y equal to, sure, the quotient e to the cosine of x divided by, instead of writing the square root of x squared plus 1, I'll do you a favor and write x squared plus 1 to the 1/2 power. So now you're going to have to use the quotient rule, and within each derivative in your quotient rule, you're going to have to use the chain rule. So I'll just help out a little bit here. If we're thinking of this as f over g, then our derivative should look like the derivative of f times g minus f times the derivative of g all over g squared. Go for it. All right, let's take a look here. So you don't really have to do this work off to the side, but it's always kind of nice to think about, okay, if we're thinking about taking the derivative of e to the cosine x, we know it's going to be e to the cosine x times the derivative of cosine, which is negative sine of x. And similarly, for the g part, which is x squared plus 1 to the 1/2, the derivative of something to the 1/2 is 1/2 times or something to the negative 1/2 times the derivative of the inside, which is 2x. So when we start writing this out, we can say that our y prime here is equal to the bottom, x squared plus 1 to the 1/2, times the derivative of the top, which we already wrote over here, is e to the cosine x times negative sine x, minus, now we switch it up, it's our function f, which is e to the cosine x, times the derivative of the bottom, which is going to be 1/2 times x squared plus 1 to the negative 1/2 times 2x. And if I was going to write this out, I would observe that the 1/2 times 2 is a 1, so we don't have to write both of them. I'd probably just write it as x squared plus 1 to the negative 1/2 times x. And then on the bottom, it's going to be x squared plus 1 to the 1/2 squared, which I would really just rather write as x squared plus 1. If you square a square root, you just get the stuff inside. A couple notes here. One, this is really gross to simplify. It can be simplified, it probably should be simplified, but we're not going to. The other thing I'll point out is if you wanted to, although I don't recommend this, if you wanted to, you could never use the quotient rule again. You could take any quotient and always rewrite it as a product. We could, if we wanted to, and again, I don't think this is necessary, but I'll just show you that you could write this as e to the cosine of x times x squared plus 1 to the negative 1/2. And we bring that up from the bottom, the power changes from positive to negative. And then if we wanted to take the derivative, we could do it using the product rule and say, okay, it's the derivative of the first thing, which is e to the cosine of x times negative sine of x times the second thing. There's a tendency right there for you. Times the other thing, x squared plus 1 to the negative 1/2 plus, and then we switch it. We leave the e to the cosine x alone, and we take the derivative of that, which is now going to be negative 1/2 times our stuff to the negative 1/2 minus 1, which is negative 3/2, multiplied by the derivative of the inside, which is 2x. Either one of these answers is completely acceptable. They look a bit different, but they are the same. Sometimes it feels very useful to avoid using the quotient rule. Sometimes it doesn't. Sometimes it really feels terrible to do it this way, and you'd rather have left it alone and done it using the quotient rule. So it kind of depends on what you're seeing. I would say most of the time, you probably just want to use the quotient rule if it's written as a quotient, but be aware you can always do this. All right, let's do a few more. So kind of one of the hard parts I would say about putting all the things together is kind of knowing which rule gets applied first. Yeah, like in this next example. Let me do that direction. Yeah.
Why is it plus e to the cosine?
So if I'm using the product rule instead of the chain rule, so the quotient rule, I'm thinking that this is my f, this is my g, this is my f prime times g plus f times g prime. I will point out though, just so everyone can see it, you really are getting the same stuff, right? Here I have an x squared plus 1 times an e to the cosine x times the negative sine x. And yeah, the power looks a little bit weird, but if you divided that by that, you would get the power of negative 1/2. And over here, even though it has a minus sign here, we actually would have a minus sign here because there's a negative right there that would come out in front. And you have an e to the cosine x. The 2's cancel, you have an x. And then you have x squared plus 1 to the minus 1/2 divided by x squared plus 1 to the 1 would give you an x squared plus 1 to the minus 3/2. So they really are the same. They're just written a little bit differently. All right. So let's look at this next one. As you might have noticed, it's important to practice this, right? We're doing a lot of chain rule problems just so we can keep seeing and getting exposed to and be like, okay, this is how we do it. It's always differentiate the outer function, leave the inside stuff alone, multiply by the derivative of the inside. And then there might also be quotient rule, product rule, other rules involved. Let's look at this one. Yeah, oh, we should do that too. Yeah. We'll get there. Sorry, I lost my spot. One second. There we go. Let's say our function is f of t equal to t cubed over 1 minus t all raised to the 5th power. So I see both a quotient and a chain rule, but now the chain rule part has to happen first. Because if I look at this, I see some stuff raised to the 5th power. And then at the end of the process, when I take the derivative of the inside stuff, that's when we'll have to use the quotient because the inside is a quotient. So we're going to write this, or we're going to start taking the derivative as, so I've got some stuff to the 5th. That's going to be 5 times my stuff to the 4th power. And then at this point, I might just write times the derivative of the inside stuff, just to save myself some mental energy there for a second. And now I'm ready to go on and say, okay, now let's finish it by actually taking the derivative of that quotient. So the 5 times t cubed over 1 minus t raised to the 4th still stays out in front. And now if we take the derivative of this, we're going to use the quotient rule. So it's going to be the bottom times the derivative of the top, which is 3t squared, minus the top, times the derivative of the bottom, which is negative 1, divided by the denominator squared. Yeah. Uh-huh. Now, I will point out, if you wanted to, you could have rewritten this as, you could have taken the top to the fifth power and the bottom to the fifth power, and t cubed to the fifth is t to the 15th. You could have simplified it this way first, and then used the quotient rule, and had the bottom times the derivative of the top minus the top times the derivative of the bottom. You would need to use the chain rule for, because the derivative of 1 minus t to the fifth is 5 times 1 minus t to the fourth times the derivative of 1 minus t, which is -1. But you could do it that way first. So I'll say this often. Often it is useful to differentiate the function. So, whoa, back it up, James. It is useful to simplify the function before you differentiate it. Here, maybe not. But here's a really good example that someone was asking about earlier today. Their function, and we've kind of talked about this before, but let me remind you, their function was something like 2x to the fourth plus x squared minus 1 divided by the square root of x. And sure, you could totally use the quotient rule here, but you shouldn't, because you can much more easily just divide each term by x to the 1/2. So it really, really pays to simplify this as 2x to the fourth over x to the 1/2 plus x squared over x to the 1/2 minus 1 over x to the 1/2. And then simplify each of those fractions as, well, let's see, if we subtract the powers, 4 minus 1/2 is 3.5 or 7/2. So we get 2 times x to the 7/2 power plus x to the 2 minus 1/2 is 3/2, and minus 1, and x to the 1/2 on the bottom comes up as x to the -1/2. If you don't like doing it this way, I'll point out you have another option to see it. You could also think of it as 2x to the fourth plus x squared minus 1. And instead of divided by x to the 1/2, it's all multiplied by x to the -1/2. But then you have to distribute that x to the -1/2 to each of your three terms. And you end up getting the same thing. You end up getting 4 minus 1/2 gives you a power of 7/2. 2 minus 1/2 gives you a power of 3/2. And -1 times x to the -1/2 just gives you a -1 times x to the -1/2. Either way you want to think of it's fine. But when you have a quotient with a single term in the denominator, whether it's x to the third, x to the 1/2, 5x squared, as long as it's one term, you don't have other things added or subtracted to it, almost always it's in your interest to make the simplification first and then find the derivative by just using the power rule and get, okay, so I'm going to get 2 times 7/2 times x to the 7/2 minus 1 is 5/2. Plus 3/2 times x to the 3/2 minus 1 is 1/2, minus 1 times -1/2 is plus 1/2. X to the -1/2 minus 1 is -3/2. And then I should have simplified this. 2 times 7/2 is definitely 7. So we get 7 times x to the 5/2 plus 3/2 x to the 1/2 plus 1/2 x to the -3/2. That's how I would write my answer. Instead of using the quotient rule, right? The quotient rule is definitely not the way to go. All right, a few more extra hard examples, and then we'll talk about some other things. But I should point out, from here on out, the chain rule is kind of always the name of the game, right? Whenever you look at a function, you should be, if you're trying to take its derivative, you should be asking yourself, is there an inner argument, an inner function that I'm going to have to multiply by its derivative at the end of the process? So you should always be on alert for, is this function a function where I would need to use the chain rule to take the derivative? And sometimes we need to use the chain rule more than once. Multiple times. Like this example. Let's say our function is sine to the 4th power of x cubed minus 1. Okay, so when you write a This is an abbreviated notation, and I find that this notation can be kind of misleading as to which function we are going to differentiate first, or what is our outermost function. So when you have a trig function to a power, I would always recommend rewriting it as the longer notation. I would rewrite this as sine of x cubed minus 1, all of that raised to the fourth power. Because now it is more obvious that we have some stuff to the fourth power as kind of our outermost function. So when we start differentiating, and yeah, I'll do this in a couple steps here. We're going to say, well, I have some stuff to the fourth power, so my derivative is going to be 4 times that stuff to the third power. And then we, of course, have to multiply by the derivative of the stuff. And then for this step, I am just going to write the derivative of sine of x cubed minus 1. But look, the thing we're now having to differentiate also requires the chain rule. We have sine of some new stuff. The derivative is going to be cosine of that new stuff multiplied by the derivative of the new stuff. So rewriting this, we still have our 4 times sine of x cubed minus 1 cubed times the derivative of sine of something is cosine of that something. And then we have to multiply by the derivative of that something, which is 3x squared. So sometimes you have to use the chain rule within the chain rule. And you can do it, technically you can do it as many times as you need to, right? You could have 6 chain rules in a row if you really had to. Like whatever, however many nested functions you have, that's how many times you have to use the chain rule. And you always just keep multiplying by the derivative of the inside functions. So you might kind of ask the question, well, how do you know when to stop? And I would say, well, when I say, for this last part here, when I'm taking the derivative of sine of some stuff, the derivative was cosine of that stuff, but then the derivative of x cubed minus 1 is just something we know directly, right? It's not something that requires a chain rule, because we know the derivative of x cubed minus 1 is 3x squared minus 0. So that's how we get to stop, by saying we know the derivative of this inside function isn't a function of a function. Let's do another example. Yeah, I'll do one, and then you guys get to do one. So let's look at this example is terrible. Yeah, good times. So our function is the square root of x plus the square root, sorry, the cube root of x plus the fourth root of x. Awful. Especially awful because we really, really, really don't like this radical notation when we're trying to take derivatives. So the first thing you should do, or that I should do, is rewrite it using, instead of radicals, using fractional roots. So this x to the 1/4, sorry, this, I already said, this fourth root of x is going to be x to the 1/4 power. Rewrite, I'm gonna do it from the inside out. So I have x to the 1/4, and then have x added to it, and then all of that stuff, the x plus x to the 1/4 should be to what new power? To the 1/3, because it's a cube root of all that stuff, and then x plus the cube root of x plus x to the 1/4 should all be raised to the 1/2 power, because it's the square root of all that stuff. But we definitely have, well, I mean, I guess you technically don't have to write it this way, but we definitely need to think of it this way. There's no other way to deal with these functions other than thinking of them as some fractional power. And now we're ready to take the derivative. Okay, working from the outside in, our outermost function is some stuff raised to the 1/2 power. So my derivative is going to be 1/2 times all that stuff to the negative 1/2, multiplied by the derivative of that inside stuff. So let's write down the inside stuff. It's x plus parentheses x plus x to the 1/4 to the 1/3. I kind of like to underline the stuff I'm about to take through. So this stuff now, this x plus parentheses x plus x to the 1/4 to the 1/3, now that's what we have to take the derivative of. All right, so let's do it. The derivative of x is straightforward. It's 1. But the derivative of this stuff to the 1/3 power, well, again, I have to use the chain rule again. I have something to the 1/3, its derivative is going to be 1/3 times that something, which is x plus x to the 1/4, to the negative 2/3 power. Because 1/3 minus 1 is negative 2/3. And then we have to multiply this by the derivative of the inside. The derivative of the x plus x to the 1/4, which is going to be 1 plus the derivative of x to the 1/4 is 1/4 times x to the negative 3/4. Close that parenthesis. Close that parenthesis. Pretty gnarly. All right, you did it. Let's do one more. Well, let's have you all do one more. So why don't you all try this one? I want you to find if our function g of x is equal to tangent of sine of e to the x to the 4th plus 2, I want you to find the derivative of that. So you kind of have three layers here, I think. You're gonna have to take the derivative of tangent, which is secant squared of that stuff. And then the derivative of the inside, the derivative sine of some stuff would be cosine of that new stuff. And you have to multiply with the derivative of the inside. And the derivative of e to the x to the 4th also requires the chain rule. So I'll give you like a minute and a half to work on that. So really do try your best. The only way to get better at this is to practice it. Okay, so let's look at this piece to the problem. Outermost function is tangent of all that stuff. So we know our derivative is going to be secant squared of all that stuff. Our stuff being sine of e to the x to the 4th plus 2. But now we have to multiply by the derivative of the inside stuff, which is going to be, well, the derivative sine of x is cosine of x. So the derivative sine of some stuff is cosine of that stuff multiplied by, I said, so one thing I often say is I said the magic word stuff. If I say the word stuff, it means I'm going to have to multiply by the derivative of that stuff. It's just kind of ingrained in my body that when I say the word stuff, oh yeah, we're multiplying by the derivative of the stuff every time. So I said cosine of some stuff, we have to multiply by the derivative of e to the x to the 4th plus 2. All right, but e to the x to the 4th is e to some stuff. So the derivative of e to the x to the 4th is going to be, well, the derivative of e to the stuff is e to the stuff times the derivative of that stuff, which is 4x cubed, plus the derivative of 2, which is 0, so we're not going to write it. And I didn't put parentheses around the 4x cubed because it's just one term, but they could have. So I should point out, for this thing I underlined here, for this stuff, all of this is the derivative of that stuff. And let's see a little bit more here. For this here, for this new stuff, all of this is the derivative of that new stuff. Yeah, there's one more thing I just thought of, which I should mention. So there's two ways to kind of attack this next thing I'm going to say. One of them comes up a little bit later on, so we'll circle back around to this. But for now, I just want to ask you, how would I take the derivative of 3 to the x? Well, I can't use the power rule because the power rule isn't for an exponential function like 3 to the x. The power rule is for x to a number. So when you have an exponential function, well, I will point out 3 to the x is a lot like e to the x. If you graph both of them, they look very, very similar. They both have that typical exponential graph shape. In fact, we can graph both of them. I'm not going to graph them very well, but here's my e to the x, and just a little bit steeper is my 3 to the x. What I really want you to know here is that when functions are similar to each other, they have similar derivatives, right? Both of these functions have the same sort of behavior. Their derivative, aka their rate of change, or the slopes of their tangent lines, should behave in a similar fashion. So that's all well and good, but how do we deal with this? Well, one way of dealing with this is to do the following thing. We're going to rewrite this as the derivative of e to the natural log of 3 to the x. This is a common way of getting around having an exponent or a base that's problematic. I'll remind everybody, when you do e to the natural log of some stuff, the e and the natural log could undo each other, so these really are equal to each other. E to the natural log of 3 to the x, you can think of those undoing each other and just getting back 3 to the x. But now, we're going to use the rules of logarithms that says, oh, I have the natural log of something to a power, that power can come down in front of the natural log. So we're going to rewrite this as the derivative of e to the x times natural log of 3. Quick question off to the side. What's the derivative of x times 7? Which I know is never how I would actually write it, but I'm writing it like that on purpose. What's the derivative of x times 7? Everybody. 7. Or even kind of more weirdly, what's the derivative of x times pi? Just pi. Because whenever you differentiate a constant times x, you just get that constant. Okay, hold on to that thought. When we differentiate e to the stuff, just like before, the derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. So here we're going to get e to the x times natural log of 3 times the derivative of x times natural log of 3. And natural log of 3 is a constant. It's about, I don't know, 1 point something. I don't really care what it is. It's 1 point something. But it's a number that never changes. It's not, there's no variable there. So when we differentiate this x times a constant, just like here and here, we're just going to get that constant. So this ends up equaling e to the x times natural log of 3 times the constant natural log of 3. Now, one more thing. We don't ever leave it like this. There's a better way to write it because I'll point out e to the x times natural log of 3 was the same as e to the natural log of 3 to the x was the same as 3 to the x. So the way we actually like to write the answer here is that this is equal to 3 to the x times natural log of 3. Hopefully this doesn't surprise you too much because we know the derivative of e to the x is e to the x. And if we say that 3 to the x is similar to e to the x, then it should have a similar derivative, meaning since e to the x's derivative has itself show up again, we would expect that the derivative of 3 to the x, 3 to the x would also show up again. And that's true for any kind of exponential function. If you have some constant base raised to some power and you take the derivative of that, that thing always shows back up exactly as is. And then you have to multiply by some stuff after that. So I will actually add one rule to our list of derivative rules, and it's the following. So for any base b that is not equal to 0, sorry, not equal to 1 and greater than 0, because we don't like negative bases, they're problematic. The derivative of b to the x power is going to be b to the x times the natural log of that base. It's also why we don't want a negative base, because you can't take a natural log of a negative number or 0. Cool. All right. A few more things to say about the chain rule here. So I feel like we've seen a lot of examples of the chain rule, and we know that you differentiate the outside function, you leave the inside stuff alone, you multiply by the derivative of the inside. There are a couple formulas I should make you aware of just so that you've seen them and you're aware of them, because they do kind of come up sometimes. So, bless you. There are, I want to say here, yeah, two versions of the chain rule that we should be aware of. I will say they both mean the same thing, they just are written in different ways. So let's look at this first example. Let's say our function is y equal to x cubed plus 1 to the 6th power. So one way to think of this, and this is kind of the thing I was saying before where you could do it this longer way, we're going to do it the longer way here. So we're going to say that the inside stuff is u. We're going to say that u is x cubed plus 1. And then just so we know, the derivative of u, which you can either write as du dx or as u prime, is going to be 3x squared. But then we can rewrite our function. We can say instead of thinking of y as x cubed plus 1 to the 6th, we can say that y is equal to just u to the 6th. And then if we take the derivative of y, well, that's an interesting thing to say, the derivative of y. What do I mean when I say the derivative of y? I need to be more specific. So I'll point out that if I differentiate y with respect to u, I end up getting 6u to the 5th. But if I want to take the actual derivative of y with respect to x, because that was the original functional relationship, here's what we get. We get the dy dx. Okay, what I'm really going to do here is actually just do it the way I like to do it, and then think about filling in the rest. So I know the derivative of dy dx is going to be 6 times my stuff to the 5th power times the derivative of my stuff, which is going to be 6 times u to the 5th times my du dx, or my 3x squared. What I want us to think of here is, oh, this is my dy du times du dx. So it's not wrong, and I really want to make sure that it looks like a y there. Although these aren't fractions, even though we write them like fractions, they act like fractions in almost every conceivable way. So if you wanted to, you could totally think of, oh yeah, the du's just cancel out, and you get dy over dx, which is the derivative of y with respect to x. And that totally is a valid way of thinking of it. So here, simplifying this all the way, or rewriting, I should say, we're going to get 6 times our u to the 5th power times our 3x squared. And our u was x cubed plus 1. So yes, we took the longest route possible to get there, but we're still getting the same result we expected to. We differentiated something to the 6th power. We got 6 times our something to the 5th times the derivative or inside something. So this is one way of writing the chain rule, which becomes useful often when we are doing implicit differentiation. And then the other way is the way I prefer to think of it, which is if we think of, sure, I'm going to write more things here. The other way to think of this is by saying well, we're going to let, again, for y equals x cubed plus 1 to the 6th. And really, I feel like this is really overkill here, but I want to make sure we're all cool with it. We're going to say, we're going to let f of x equal x to the 6th. So it's like f is our outer function, and g of x is the inner function, x cubed plus 1. We know that f prime of x is 6x to the 5th, and g prime of x is 3x squared. And then if we rewrite this as f of g of x equal to x cubed plus 1 to the 6th, then our derivative is going to be the derivative of f of g of x, which using the official like chain rule formula, it's the same thing we've been saying this whole time. It's the derivative of the outer function, leave the inside stuff alone, multiply by the derivative of the inside stuff. I'm going to say it like 100 more times probably, but that's the idea. So f prime is x to the 6th, but it's not x to the 6th. It's not x to the 6th we're going to get. It's going to be g of x to the 6th power, because that's what f prime of g of x is. F prime of, oh, nope. It's not, I wrote f of g of x. Sorry, that's a mistake. Let's try again. F prime of x is 6x to the 5th. So f prime of g of x should be 6 times g of x to the 5th multiplied by g prime, which is then going to give us 6 times our g of x, which is x cubed plus 1 to the 5th power, times g prime, which is 3x squared. And yes, it's exactly the same as doing it the other way. And it's all the same as doing it the way we've talked about it this whole time. So it's good to know these formulas. They do come up sometimes in some contexts. But if you're just differentiating functions, I would say conceptualizing it the way we've been talking about this whole time is probably the best way to go. But sometimes, sometimes people are going to throw problems at you like the following, where they don't actually tell you what the functions are. So someone might give you something like this. Suppose that we know that h of x is equal to f of g of x, and we're told that f prime of 2 is equal to 5. F prime of negative 3 is equal to negative 7, sorry, positive 7. F prime of 4 is equal to 6. G prime of G of negative 3 is equal to 2. G prime of negative 3 is equal to 4. And then they say find H prime of negative 3. And it's not always the case, but sometimes when someone throws a problem at you like this, some of this information here will be extraneous. You don't always necessarily need every bit of information they've given you. Sometimes they're just trying to make you think you do. They're trying to trick you sometimes. So I want to find h prime of negative 3. So what I'm trying to find is, I'm going to first just think about finding h prime of x. I'm just going to write it out in terms of x. And then after I've written out the derivative the long way, I'm then going to plug in the value of x I need, which in this case will be negative 3. So my h prime of x is going to be, well, it's just the derivative of f of g of x, which is going to be f prime of g of x times g prime of x. And now I'm going to plug in negative 3. So I have h prime of negative 3 equal to f prime of g of negative 3 times g prime of negative 3. And now I start looking at what's given to me so I can start replacing things with numbers. So g of negative 3 is equal to 2. So this part here is going to become f prime of 2. And g prime of negative 3 is equal to 4. And then f prime of 2 is equal to 5. That's going to be 5 times 4, which is 20. So I didn't use like 2 of the things they gave me there. That's fine. I didn't need to. what else can we ask about here? Sure, let's do that too. So there's a couple other questions we could ask. Something like, what if I wanted to find here, let's say that that's part A. Do I have all the information I need? Let me make sure. I don't think I do. I need to give you one more piece of information. Let's also say that f of -3 is equal to 6. So now I'd like to find the derivative of f times g of x. I will say be careful. What do I mean by this? Well, what I wrote there was the product of f and g. But I'll just make sure everybody knows this f dot g of x means f of x times g of x. On the other hand, if I wrote f circle g of x, that's another notation for function composition. That means f of g of x. So this is f of g of x. So when you're looking at these things, make sure you are aware of what's actually being written because it can be easy to miss that circle we're not looking for. So here, if I want to find the derivative of this, well, I'm going to use the product rule. Oh, I forgot to say one thing though. I want to find the derivative of this evaluated at x equal to -3. So let's just find the derivative of the product first. We're just really writing down the product rule. We know that the derivative of f times g is equal to f prime of x times g of x plus f of x times g prime of x. And now if we plug in 3, the derivative of the product f times g of x evaluated at x equal to -3 is just going to be, we're just going to plug in -3 everywhere. F prime of -3 times g of -3 plus f of -3 times g prime of -3. And then we look at our table to find the values. F prime of -3 is 7. G of -3 is 2. F of -3 is 6. G prime of -3 is 4. And then we get 7 times 2, which is 14, plus 6 times 4, which is 24. And 14 plus 24 is 38. Let's do one more like this because there's a funky homework one that I want to look at. We'll get one more, sure. So let's say still the same idea here. So we're told that we only need the following two pieces of information. F of -3 is equal to 6. Am I gonna like that? Yeah, sure, it's fine. And f prime of -3 is equal to 7. It's gonna be gross, but fine. So now here's what we're being asked to find. We want to find the derivative of f of x cubed minus f of x over x squared plus 1. Evaluated at, well, there's only one option. Evaluated at where? What's the x we have to be plugging in if we're going to do this problem? It's got to be -3. There's no other options here. So again, for any problem like this, where they haven't actually given you the function, but they just told you, here's a formula, differentiate it, and then plug in this number, you always want to do the derivative without plugging in the number first, I think. So I'm just going to take the derivative of this whole thing, and then after that, I'll plug in -3. So this is going to be equal to, well, I got some chain rule going on here. The derivative of something cubed is 3 times my something squared times the derivative of that something. Minus, for this quotient here, we're going to have to use the quotient rule. So it's going to be the bottom, x squared plus 1, times the derivative of the top, which is just f prime of x, minus the top, f of x, times the derivative of the bottom, which is 2x, all divided by the denominator, squared. Now we can plug in our -3. So my derivative, I'm going to call this y prime. My dy dx or y prime evaluated to x equal to -3. So the downside to doing it the way I'm doing it is a lot more writing. You probably could have just plugged the -3 here and had to write less. Oh well, sometimes you write more. We're going to get 3 times f of -3 squared times f prime of -3 minus -3 squared plus 1 times f prime of -3 minus f of -3 times 2 times -3 over -3 squared plus 1 squared. And now the rest is plugging things in and simplifying. So we're going to get, so f of -3 is 6, f prime of -3 is 7. So we're going to get 3 times 6 squared times 7 minus this gross fraction over here. 9 plus 1 is 10 times f prime of -3 is 7 minus f of -3 is 6 times 2 times -3 is times -6. All divided by 9 plus 1, which is 10 squared. And then the rest of this is doing some arithmetic, which is not super nice, but fine. Sure, that's 36 times 3 is 108 times 7 is 756 minus 70 plus 36 is 106 over 100. So if you really wanted to write this out, it's 756 minus 1.06, which is 754.94. That seems silly. You should just leave your answer like this. And my numbers were not great. Usually when these problems are asked, the numbers are not quite so heinous as the ones I just made up, but that's the whole idea. You should take the derivative in whatever way you can using usually a combination of the product, quotient, and chain rule. And then after you've done that, then you plug in the x value you're plugging in, you plug in all the associated values and simplify if you want. Or if it's web work, don't simplify. Type in this gross thing here and let web work do the simplifying for you. Now, I would say if I was typing this in, I would probably write it as like 21 times 36 minus 70 plus 36 over 100, right? I can do some of the it's much easier to type in 70 minus 30 plus 36 over 100 than 10 times 7 minus 6 times -6 over 10 squared, right? Do the little simplifications that are easy so you don't have to type in really, really gross things. That's my opinion. All right, where are we at? Oh yeah, you should do that. Okay. We got what, 15 minutes? 14 minutes? Sure. So let's spend the last few minutes here talking a little bit about implicit differentiation. That's certainly what's coming up next, or some of you are already getting to. So implicit differentiation. Differentiation. The big picture idea here is that we're going to have some equations where we cannot solve for y. And the idea is we're going to take the derivative of these and just assume that y is a function of x. So kind of like here in this previous problem, where we differentiated f of x cubed and got 3 times f of x squared times the derivative of f of x. The same thing's going to be true if we differentiate something like y cubed. We're going to get 3 times y squared times dy dx, or y prime, because we're making the implicit, that's why it's called implicit differentiation, assumption that y is a function of x, even if it actually isn't. But let's back it up a little bit and start with this very, very typical example here. Sure. So let's say that we want to find the slope of the line tangent to the circle x squared plus y squared equal to 25 at the point 3 comma -4, which is definitely a point on that circle. So we're going to graph it. It doesn't have to be a very good graph, but here's our circle. And 1, 2, 3, 4, 5, 6, 3, -4, about right there. So there's our point of tangency at 3, comma, -4. And we're trying to find, we want to know the slope of that line. So one way to do this is to not use implicit differentiation at all. It's just to solve for y and then take the derivative, which is totally valid. I'm going to make a little mistake along the way. We're going to fix it, so it's going to be fine. But I'm going to make an error to point something out. So if we try to solve for y here, we get y squared equal to 25 minus x squared. And we take the square root of both sides, and we get y equal to the square root of 25 minus x squared. Or since I know I want to take the derivative, I'm going to write it as y equal to 25 minus x squared to the 1/2 power. Now we'll take the derivative to find the slope. My derivative here is going to be 1/2 times 25 minus x squared to the -1/2 times the derivative of the inside, which is -2x. And I do think it's worthwhile to simplify this. The 2's cancel. And I can rewrite this as dy dx equal to, I have a -x on top. And instead of writing 25 minus x squared to the -1/2, I'm going to put that on the bottom as 25 minus x squared to the +1/2, or actually preferably the square root of 25 minus x squared. And now if I plug in x equal to 3, because that's the x value at the point of tangency, I'm going to get the wrong answer. It's okay, we're going to fix it, but I want to point something out. So if I plug in x equal to 3, I get -3 over the square root of 25 minus 3 squared. 25 minus 9 is 16. The square root of 16 is 4. So we get -3/4. Let me ask you, does our tangent line look like it has a negative slope? No, it doesn't. It very much looks like it has a positive slope. So here's the problem with what I've done here. And we're going to fix this mistake in a second here. I didn't pay attention to solving for y. And the thing is, that circle, not a function. It fails the vertical line test very, very much. So when we took the square root here, we really should have had a y equals plus or minus the square root of 25 minus x squared, where the top half is the positive square root of 25 minus x squared, and the bottom half is the negative square root of 25 minus x squared. And since our point of tangency is on the bottom half of the circle, we have to be using the negative square root of 25 minus x squared instead of the positive square root. So there should have been actually a negative here, a negative here, which cancels the negative there. That's a positive, that's a positive, that's a positive. And now our answer makes sense. That slope of the tangent line is certainly a positive slope because we're increasing from left to right, and it is positive 3/4. The good news is that if we had used implicit differentiation like we're about to, we wouldn't have even had to worry about which piece of the graph we're using, because the implicit part's going to take care of that for us. So let's do it again, but different. So again, but different. So our equation was x squared plus y squared equal to 25. And when you're using implicit differentiation, almost always the first step is to take the derivative of both sides. Now, one quick aside here, if your original expression is a fraction equal to some other stuff, so it's always an equation, right? If you're doing implicit, it's always something equal to something else. If your original thing is a fraction, it is valid and useful to get rid of the fraction by multiplying both sides by the denominator. So if you ever see that case where you're using implicit and you start off with a fraction, don't differentiate a fraction. Multiply both sides by the denominator and then take the derivative of both sides of that. It's easier. But here we don't have that problem. So if I take the derivative of both sides, so differentiate both sides. So x is just x. The derivative of x squared is 2x. How nice. But y, we're imagining that y is a function of x. So the derivative of y squared is going to be 2 times y to the first times the derivative of the stuff. So right here, we're imagining that y is equal to some function of x, and that the derivative of f of x squared is equal to 2 times our f of x to the first power times the derivative of the inside stuff. That's what's happening right there. We're just writing it in a simpler way. On the right-hand side, what should I have? Ooh, good question. We're taking the derivative of both sides. The derivative of 25 is going to be 0. You be careful though, because for whatever reason, people often forget that we're doing it to both sides. And I've seen many, many students over the years write 25 there instead of 0. Because they're like, oh, it's just 20. No, it's the derivative of 25, which is 0. And now we're going to solve for the derivative. So we're going to isolate this dy dx here. I'm solving for dy dx. I'm going to subtract 2x first. So 2y times dy dx equals negative 2x. And then dividing by 2y, my derivative dy dx is going to equal negative 2x divided by 2y, which canceling the 2's, my derivative is negative x over y. A couple neat things here. If we went back and actually plugged in the thing we solved for y for before, y being equal to that, you would exactly get the same derivative we had right here. If I plugged in negative square root of x of 25 minus x squared in the bottom there, we'd have exactly x over the square root of 25 minus x squared, because the negatives would cancel out. Cool. We don't need to do that. We're not trying to find the derivative everywhere. We're trying to find the derivative at the point. So I want to find the derivative dy dx evaluated at the point 3, negative 4. And since I have both the x and y coordinate, I can plug those in for x and y. And I'm going to get negative 3 over negative 4, which is positive 3/4, just like we got here. So a couple things. This was kind of a unique example in that we were able to solve for y. Most of the time with implicit differentiation, you can't solve for y. You're just stuck with some gross equation that has x and y all mixed up together, and our job is to find the derivative. Let's look at one more example, because I think that's all we have time for. So the important thing to remember with implicit differentiation is that we are making the assumption that y is a function of x. So, for example, we could say find dy dx for the equation x cubed plus y to the 4th equals 2x squared y cubed plus sorry, my brain went away, plus e to the y minus 1. All right. So here's our job. Our job is to take the derivative of both sides, remembering that y is a function of x. So the derivative of x cubed, straightforward. It's going to be 3x squared. The derivative of some stuff to the 4th power, a little bit less straightforward. It's going to be 4 times our stuff cubed times the derivative of our stuff. What I really should have said is implicit differentiation is just another example of using the chain rule. Every time you've got y to the some power or something with y in it, we're just imagining that y is some function of x, some stuff that we then have to multiply by its derivative. On the right-hand side, I have the product 2x squared times y cubed. So I'm going to take the derivative using the product rule. The derivative of 2x squared is 4x. Leave the other piece alone. Multiply by, leave 2x squared alone. And the derivative of y cubed is going to be, well, the derivative of some stuff cubed is 3 times my stuff squared times the derivative of my stuff. Finally, the derivative of e to the stuff is e to the stuff times the derivative of that stuff. And the derivative of y minus 1 is the derivative of y minus 0. So it's dy dx. People always get kind of tripped up by that. So if I'm taking the derivative of y, The derivative of y is the derivative of y, which is dy dx. The derivative of 1 is 0, so I don't subtract anything. So it can be a little bit weird. Some people say the derivative of y is 1, but they have to multiply by dy dx. That's another way you can think of it. But I really would encourage you to say, if you're just taking the derivative of y, you just get the derivative of y. Which kind of feels silly, but it's the truth. And now, after we've done this first step, the rest of this is algebra. We have to collect all the dy dx terms on one side and everything else on the other side. So we're going to write this as 4y cubed times dy dx minus 6x squared y squared times dy dx. Yes, I did some simplifying there. Minus e to the y minus 1 times dy dx equal to 4xy cubed minus 3x squared. On the side with the dy dx's, we factor out the dy dx. That's why we got all of them on the same side. So we've got dy dx times 4y cubed minus 6x squared y squared minus e to the y minus 1 equal to still 4xy cubed minus 3x squared. Finally, we divide by all of that to get dy dx all by itself equal to 4xy cubed minus 3x squared over 4y cubed minus 6x squared y squared minus e to the y minus 1. And that's the general process for finding a derivative implicitly. You take the derivative of both sides, you put all the dy dx terms on one side, all the other terms on the other side, you factor out the dy dx, you divide by what's multiplying the dy dx times by dy dx. That's how it works. We'll talk more about it next week on Tuesday.